So yeah, thanks everybody for joining us today as part of another session in the complex training series. Um, Again, as Cindy said, my name is Marty Candice. I work in the HPC User Services Group, and today's topic is essentially an introduction to getting started with batch job scheduling using Slurm, which is sort of one of the most popular batch job schedulers out there. So if you're new to Slurm, this is probably like the perfect talk for you. If you've sort of already familiar with working on Slurm, maybe you'll pick up a few new tips here and there. But it's really intended to be an introduction to Slurm for new users. If this is your first time joining us as part of the Complex Training Series, this is a new training program that started a little over, I think, a year and a half now, almost finishing up 2 years at the end of the year, to cover topics in sort of high performance computing for users who are not traditionally programming focused, right? So if you're not developing your own code, the idea is to really cover topics that, sort of every user of an HPC system would need to understand, such as parallel computing concepts, different types of Linux tools and shell scripting, a little bit about security, batch job scheduling, which we'll cover today, and sort of data management, stuff like that. So if you're new, there's a whole host of different topics and training material that we've been developing since the program started. And as Cindy, I think, provided the link, or it's also at the first slide, there's a link to some PDFs of the training material and slides for each topic that we've covered so far. I am monitoring the meeting chats as we go, so I'll try and stop and take any questions as we go along. But I'll also try to stick to covering the slides material within the hour, and then at the end of every complex webinar, we have a 30-minute sort of Q&A session for people who want to stick around and ask additional questions. But if you can't stick around and need to ask a question during while I'm talking, feel free to drop those questions into the chat, and I'll try to address them as quickly as I can. So today's session is, as I mentioned, getting started with batch job scheduling with Slurm. But this is sort of part of a 3-part sort of batch computing series that we've been putting together. And I've put links here to the other talks. One is sort of getting familiar with the Linux scheduler if you've never sort of directly interacted with it before. It's sort of the idea for that talk. And then some high throughput and many task computing workflows. So this is sort of a follow on to today's talk, where cover a little bit more advanced features in Slurm, such as job arrays, sort of throttling job arrays, and sort of developing more complicated workflows. So it sort of extends some of the material beyond this talk. So if you're interested in that after today, that's sort of the one I would recommend going to after this. Okay, so today's talk, the learning goals are really to teach you about what a batch job is, sort of what is Slurm, sort of what are the components, and some of the commands that you'll use to interact with Slurm. And then we really end with a series of examples sort of demonstrating sort of the key components of writing a batch job, submitting those jobs to the scheduler, and sort of just getting up and running on a Slurm batch job scheduler for any of the HPC resources you might have access to. And the reason we focus on Slurm is it's pretty much the most popular batch scheduler out there for HPC systems. I think if you look at the statistics, it's like at least 60% of most HPC systems run Slurm these days. So if you're new to Slurm, it's a good thing to learn how to use. Okay. So this is sort of the table of contents for the plan today. I want to do a brief just overview of HPC hardware and system architecture. We touch on this on a lot of the complex webinars and slides, just to set the stage again for context of the different types of components that we interact with when we talk about running on an HPC system. So it's just a quick reminder of the different hardware and different node types and things that you'll interact with on these systems. And then we'll again talk about batch job scheduling in general, just some of the general concepts and terminology, and then we'll jump into some of the commands that you'll use to interact with Slurm itself, about how to get information about your jobs, how to get information about the different nodes and partitions that are part of the Slurm cluster you might be working on. And then again, as I mentioned, really focused on at the end of how to sort of start writing and structuring and submitting your batch jobs to Slurm, and sort of the different commands you'll use to interact with the scheduler when you're running batch jobs on these systems. Okay, and then highlight some best practices, and then we'll go into that 30-minute Q&A that I mentioned. Okay, let's see. Okay, about 10 minutes in. Okay. So this is sort of what an HPC compute node looks like, right? So these clusters are all sort of built out of many different nodes, essentially. And each node is complicated enough in itself where it has multiple different CPUs, and each CPU is in a socket. So sometimes most of these HPC nodes, as you can kind of see here in the lower right-hand side in sort of the cartoon diagrams, there'll usually be two different sockets, so two different CPUs, so central processing units, where sort of the standard sort of programs that you'll launch will initiate from on any given compute node. But there are also, as you're probably aware, many different types of hardware accelerators that are used, most notably GPUs these days, in many different types of high-performance computing nodes, especially if you're doing any sort of AI and machine learning. There's also, in this case, we have GPU nodes on the systems that we have at SDSC, such as Expanse. This is kind of one of the node types that we have in Expanse, which I'll run the examples on today. But you can notice here, even with a specific type of HPC node, there's all this complexity, and even the interconnects of how the CPUs and GPUs are connected to each other, even in the same type of node type from a vendor, can be slightly different. That's what these schematics at the bottom right are kind of showing, right? Of how the interconnects and how the CPUs will communicate with the accelerators and the node type. It will vary depending on the type of system that you're on. So this slide is really just to highlight, if you're not familiar with some of the different types of pieces that go into what makes up these nodes, this is kind of a good place to start thinking about some of the hardware that are in these things, that if you aren't familiar with them, to get familiar with them, because it really will matter at some level depending on the types of codes you're running, especially if you're doing any large parallel computing work. Understanding sort of how the hardware that you're interacting with is laid out is going to be important for performance long term. So we have HPC node. An HPC system is made up of a bunch of those nodes. Those nodes are usually organized into what we call racks. And so you can see this is sort of overall system architecture of Expanse at SDSC. So this is our main production supercomputer right now, part of the Access program funded by the NSF. And each of these racks on Expanse, for example, is made up of 52 individual compute nodes that are only contain CPUs, and then we also have in each rack 4 GPU accelerated nodes. So in most HPC systems you'll interact with, there's going to be multiple node types as well, that you might do computing on, right? If you have a GPU accelerated code, you'll want to use those GPU accelerated nodes. Obviously, if you don't have something that can utilize GPUs or any sort of hardware accelerators that might be available, the standard sort of CPU only nodes is kind of what you would be targeting, right? But understanding, the different types of node types on any system you're interacting with is important to take into consideration, right? And you'll see that today in some of the examples when you start asking for resources in Slurm, right? There's going to be these things called partitions, which are how the scheduler organizes understanding the different types of node types and the different type of limitations that the system administrators that have set up the scheduler to run your jobs on these resources. The different constraints and different types of requests you can make are sort of all tied to the physical hardware itself, but also sort of the policies in place that the system administrators have designed for how they expect jobs to be scheduled and run on these systems, right? So there is a sort of a mapping between the physical sort of hardware and design of the system to also how you'll see things in the scheduler today itself. Anyway, this is kind of just a high-level overview of what an HPC system architecture looks like. There's a lot of detail here. It's a little bit, beyond what we really need to understand today. But what I like to remind people of is sort of you need to really have at least a simple conceptual model of what an HPC system looks like. And this is sort of my simple schematic diagram of the important parts to remember about an HPC system when you're interacting with it. And we'll use this reference model sort of to understand sort of how and where, you'll be interacting with Slurm on the system and what parts of an HPC system in this sort of cartoon schematic will be sort of laid out essentially. So you have the login nodes, that's sort of the front door to the system, right? This is where you sort of access the HPC system from your personal computer or maybe a lab workstation over the public internet. Beyond that, the compute nodes, that's where the computational workloads run, right? That's where the business end, where you actually want to get your code running or your data analysis running, some sort of visualization. That's where the main compute workload that will run, right? Of course, with all of these individual compute nodes, there's networks that connect them. So if you're doing sort of distributed parallel computing across multiple compute nodes, right, you usually have a high bandwidth, low latency network between those nodes, but there's also usually other internal network interfaces that go to the different shared file systems where you'll be storing data, reading and writing data, or even doing data transfers to. And then there's a set of management nodes, and this is like where the core parts of the batch job scheduler will run, for example. But yeah, so that's sort of the main set of node types that are available in an HPC system that you'll sort of interact with at any given time. Okay, so that was just a quick overview of what an HPC system is, the different types of node types you might see. So jump into batch job scheduling. So what is batch job processing, right? So when we talk about computing, we usually talk about sort of interactive computing and batch computing on these systems. So interactive computing is sort of what you're most familiar with, right, on your personal computer, right? If you're using a web browser, you're sort of running an application that is accepting input from you as you utilize that application, right? It's sort of live running and it's responding to your interaction with that application, right? And there are interactive applications that you might use in an HPC environment. Most notably, a lot of people these days very popular using things like VS Code to sort of develop your applications sort of natively in the environment that you're then going to run it on. I see a lot of people doing that these days, but also for people doing sort of real-time sort of data exploration. So if you have like big data sets that you want to sort of explore and run analysis on, but you don't really have a sort of fixed workflow yet that you have that you would pipeline that data in and just get sort of batch processed. There's real-time sort of data exploration, analysis, visualization applications that you might run For example, this is here I'm showing an example from ParaView, which is just a sort of 3D visualization rendering application if you're doing any sort of, say, weather simulations, or I think this is a combustion simulation on the right there. Anything sort of large 3D volume sort of rendering, it's a well-known application for that. So that's sort of an example of an interactive application you might run on these systems, just because at the end of the day, sometimes these data sets are huge, and so you can't even download them to your laptop to do the analysis on your personal computer. On the other end is what we're here for today, is getting started with batch job scheduling, so batch processing. So this is when you run an application on one of these systems without any user interaction, right? So the idea is really that you set up the scripts and the workflow in such a way that you can just submit that set of tasks and computer programs that you want to run, and it will automatically utilize the compute resources that you've specified that are needed to run that job. It's kind of sort of how we sort of refer to these sets of tasks. And there's no interaction. So it's sort of set it and forget it once you set it up, right? That's the idea of batch processing, right? And it's really used for, again, traditionally it was used for sort of automating high volume, sort of repetitive tasks, like such as data processing. But in the HPC world, I would say it really is the way that we allow the shared use of these advanced compute resources, right? We have many users all running different types of applications. While you might have a bunch of repetitive tasks or types of simulations that you need to run, sort of maybe some sort of parameter sweep using the code that you're using, we use these batch job schedulers really to share the resources among all of you, right? So the idea is, for the way we look at it, I would say is, when you're writing your job scripts and asking for the resources, we're looking at it as well. It's a way for you to request the resources you need to run your application, right? And to do it in a way that is organized and sort of gets you in line so that you have access to the resources when your turn is up, right? And so this is, it's very hard for us to offer sort of interactive computing resources, because at the end of the day, most HPC resources are oversubscribed, right? There's more users at any given time that need more CPU cycles or GPU cycles than sort of could be provided on demand, right? So you always have to sort of organize things to get the resource requests from the users, organize that, put them in a line, set them up to then run those applications without user interaction eventually, right? So what is a batch job? So if you're not familiar with what a batch job, right, it really is just this prescripted set of commands that you want to run without user interaction, right? So these commands or programs that you want to run are simply usually organized as a shell script, right? And this is an example of one shown in the terminal screen capture there. And we'll go through the different parts of um, uh, these scripts as I walk through the examples later. So I won't go into detail here, but it really is just a set of commands in a shell script that define essentially what the resources you want from the HPC system to run the set of commands that appear later in the script. Any sort of variables or commands that will help define the software environment that you need to run the application that you want to run, and then the actual sort of primary executable command that you want to run. So that's kind of what's shown here. But this is what a batch job is. The batch job scheduler is the software that takes those scripts, right, and tries to fulfill your request, right? Essentially, it knows everything about the compute resources on the HPC system that you have access to. The batch job script defines, your request for those resources and the actual commands that you want to run. The scheduler itself just controls and tracks where and when those jobs run on the system you have access to, right? So it's, how I like to, you know, describe it really is with this analogy. It really is the scheduler itself is like the air traffic control, right? If you're the user, you're like the pilot in your plane trying to, you know, run your workload. You sort of have to have a flight plan, right? That's your job script. Once your flight plan is filed, right, you get up into the job queue. And so your submitted job is sort of waiting for its turn to take off and get launched onto the HPC system by the scheduler itself, right? And go on and get your research done, right? So this is sort of the way I think it's a pretty good analogy, but yeah, this is sort of what the job schedule is. It really is that air traffic controller that's determining where and when your job is going to run on the system. Okay, so yeah, so in practice, right, the scheduler is really trying to solve this sort of, um, complicated Tetris problem, right, where you have many jobs in the system, you have many nodes in the system, and it's trying to match those jobs to the compute resources on those nodes in the system, right? And the aim of any scheduler that you might interact with really is sort of listed here, sort of really want to try to minimize the time between job submission and job completion. So you're not waiting too long for your jobs to finish, right? Because you want to get your research done, right? So every scheduler is trying to get you through the system and get your work done as fast as possible, right? But it's also trying to optimize the resource utilization, right? We're trying to not waste any compute resources for too long, right? So there's sort of that trade-off. And then you're also trying to process as many jobs as soon as possible, right? So trying to maximize what we call job throughput, right? So this is sort of the three legs of the optimization problem that any scheduler is trying to solve. However, there is also an important component that is noted here. Like in most cases, these job schedulers actually also try to employ a what's known as a fair share scheduling algorithm, right? So where essentially it's also trying to share the resources available on the system um, among the users over time, right? So if you're, for example, a user who has been running a lot of jobs lately and getting a lot of jobs through the system, if a new user comes in who's never run a job through the system, these fair share scheduling algorithms will usually give that new user a little bit higher priority than your next job because you've used the system a lot recently. They haven't used it at all, so their job might get scheduled before yours, right? So there's this other dynamic of trying to share the resources as fairly as possible over time as well. In many of these deployments, some HPC systems they might have these first come first serve type of uh, scheduling policies, but that's usually pretty rare, I would say, especially in the Access NSF HPC ecosystem. Most of them are running some sort of fair share fair share process with usually their Slurm scheduler. And then also the asterisk down here, I mentioned briefly interactive versus batch jobs, right? Or batch computing. Even if you have an interactive job, right? Maybe you want to run a Jupyter notebook and do some data analysis that way, or maybe you want to use ParaView to do some visualization, right? The one thing to remember about quote unquote interactive jobs is um, they're treated the same as batch jobs, right? So the scheduling policies when you try to submit a job or get one of these interactive jobs running for your work, you're going to wait in line just like a batch job usually, right? So most systems don't have specialized queues or partitions for interactive jobs. Some systems might, but I would say in generally it's pretty rare. Like, on our systems, if you want to run one of these interactive applications, you need to basically submit the requests, and eventually your job will start just like a batch job, right? Which means it might start immediately or in a couple minutes, or it could take hours, right? So if you need to on-demand computing resources, most HPC systems aren't like that, right? So you sort of need to plan ahead if your workflows are really more interactive needs, right? Okay. So we've talked about job scheduling in general. So let's go ahead and start looking at Slurm, right? So Slurm is a free open source distributed batch job scheduler, right? For Unix like operating systems. And it's really is, I think, 60% of the supercomputers, HPC clusters out there that you will interact with are likely using Slurm. And so if this is your first time using Slurm, it's definitely going to be a useful skill to have when you interact with these systems in the future. Kind of just like I mentioned with you know, what do batch job schedulers do in practice, right? Slurm provides all that functionality, right? It has a way to allocate compute nodes for some period of time to your jobs that you submit to the system. It has, a framework and sets of commands that you can use for starting, executing, and monitoring the progress of your jobs as they run on the allocated compute nodes that the scheduler gives you. And it has, different policies, mechanisms, and things for um, setting how the scheduler manages the queue of pending user jobs, right? So you don't really have to usually worry about that yourself, other than, you need to, any HPC system that you interact with, you kind of need to understand some of the scheduling policies and how things work. I mean, for example, obviously there's limitations on how many sort of compute cores or memory you can request from any given compute node. Usually there's always a maximum amount of time you can set for any given job that you want to run, right? But this is all controllable by the people who run the system, right? Who run the scheduler themselves. They will set these policies, and you need to sort of understand what those policies are when you make the requests for the different compute nodes that you might want to run on. And that's always usually covered in a system's user documentation, right? So you don't really have to sort of discover that yourself. It should be fairly clear from the user docs what those policies are and sort of how you begin making the right types of requests for the different types of resources you need on that system. But yeah, so that's sort of Slurm is just a batch job scheduler. There are many other batch job schedulers, and they all sort of work the same, but Slurm has just kind of become the most popular in the HPC world over last 10 plus years. So yeah, so I've shown this conceptual model in the first couple slides. Just want to remind you kind of what those different components are. So you sort of have the login nodes, the management nodes, the compute nodes, might have some shared file systems, and just want to map sort of the different parts of Slurm on the next slide to these resources, right? So this is kind of what the Slurm architecture looks like. So there's really three main components of any Slurm scheduler. And you don't necessarily need to know too much about these components, just that they exist and you're sort of interacting with them at any given time when you interact with Slurm. And they are the Slurmd. So this is a daemon. So it's a sort of long-lived program that's running on any given compute node that you're interacting with that is sort of managing the jobs that run on that compute node, right? So it is, the thing that's looking at your job and understanding if it's running or if it's, if it just failed, or or even if the node itself failed for some reason, it's sort of doing all the Slurm management of jobs and the node itself on the compute nodes, right? So every compute node has at least a Slurmd running on it. There is usually on the central sort of management nodes in an HPC cluster will be running the Slurm CTLD. So this is the central controller management daemon that is monitoring all of the Slurmds out there. So it's sort of the central hub of the this is where the air traffic control tower is essentially, right? This is where all of the Slurmds will communicate with the Slurm CTLD to update, the status of your jobs, and it'll also be the place where the request to a Slurmd goes to say, hey, please take this job and run this job from the queue. So that's sort of the tower of the air traffic controller. And then there's obviously a database somewhere that is tracking all the accounting and records of the jobs that run on the system. So there's a Slurm database daemon that sort of interacts with. I think that you can probably choose different types of databases for the Slurm DB, but those are sort of the three main system level components that are need to be running at any given time for Slurm to work, right? So on some systems, right, if you start getting errors when you're running Slurm commands, sometimes the Slurm CTLD or the database is down, or maybe something's wrong with the Slurmd even on a compute node, right? There's reasons why these processes that should be running might fail, and so it's a distributed system. It's complicated. If you see Slurm errors when you're running commands, just remember that there's the other things out there that you're communicating with that may or may not have a problem. So if you see a problem, with a Slurm command, it's something that you should usually report to the help desk for the HPC system you're working on, because they'll probably check and see if something's wrong with one of these Slurm daemons on the back end. Now, the thing that's more important for you are the user commands, which are sort of in this blue box here on the left. And I've sort of tried to list these in the order that's probably the most useful for you. So these aren't long-lived running processy daemons like the controller daemons that we just talked about that actually run Slurm as the system, but these are the commands that you have as a user to interact with those different components of Slurm, right? So sbatch is the command that you'll use to submit your job scripts to the system. sq is the command you'll use to sort of monitor the progress of your jobs in the queue. So as your jobs are pending or while they're running, it's the way to sort of get active information about, or get information about those active jobs in the system. And then scancel is kind of, those are sort of the three most common commands that I'll use, where sbatch, you submit jobs to the system. sq, you're like looking at the job and seeing what their status is. And then if you've made a mistake, scancel is a way to take your job out of the queue and sort of then go back and resubmit it once you fix the mistake you have in the job itself. So those are probably the three most common commands that even I use. But there are a few other client commands you might find useful that are sort of listed here, or not listed here. Like for example, saccount is a way to get information about jobs that are already finished. So that's sort of the command that you would use to query the Slurm DB on the back end to get information about past jobs and what Slurm knows about those jobs. For example, it'll know how long the job ran, how much, sort of how many compute nodes or CPUs or GPUs requested. Even knows what sort of the state of the job is when it finished. But yeah, so, and then sinfo is to get information about the nodes themselves. But we'll see just a quick overview of those as I sort of walk through these slides here. Okay, 20 minutes left. Okay. Yeah, so SQ is sort of the one that command that you'll probably use most frequently because people are always interested in what's my job doing? Is it running it? Is it running it? Um, but yeah, it really is just the command to query and view information about sort of active user jobs that you submitted to the system, right? So SQ itself will list usually by default all of the jobs in the system. I recommend you don't do that. So, usually all you should care about is your jobs. Remember, there's a database in the backend. There's running daemon processes. So every time you run one of these client commands, you're interacting with one of those other um, processes that are running. And so if you generate too many queries against those processes and the database in Slurm, right, it can um, just cause congestion from all of these calls to the backend processes, right? So, you want to try to limit your queries as much as possible because, you know, you know, you just don't want to pull the backend systems like incessantly, essentially, because it'll cause problems from a systems perspective when it's trying to take other user requests, right, as well, right? So it's sort of good etiquette not to pull the scheduler too often with things like SQ, right? So, and one way to limit the load on those queries is to only pull for your job. So I put a recommendation here. You can create a alias and say your bash RC or whatever shell RC file that you have to just only query your user jobs with the -u user flag here on the SQ command. Okay, so that's SQ. Sinfo is kind of the opposite side of SQ. So SQ is about jobs, which lists the job ID, the partition, the name of the job, username, the status of your job, how long the job's been running, if it's been running, the number of nodes you've requested, some information about the status of why the job may or may not be running or what node it's actually running on. On the other side, the sinfo is all about the nodes themselves. So if you, for whatever reason, need to query information about compute nodes, the sinfo command is for that. The one reason I just show this command, even though it's not as useful, I would say, from a user perspective most of the time, is that it really does show you sort of how Slurm views the compute nodes that it's managing, right? Or understands um, because at the end of the day, right, Slurm is trying to match the user jobs from that you see in the SQ command in the list there to the list of compute resources over here in the sinfo command, right? And the key thing, if you're new to Slurm, is to understand that there are different partitions, right? And we'll see that in the job scripts themselves. The partitions is how Slurm sort of divides up an HPC system, right? There is, in different schedulers, a partition is usually called a queue, but in Slurm, there's really only one queue, and then there's multiple partitions usually. A partition is just a set of resources that are that you can require. A set of resources that usually have a different set of limitations on the types of resource requests you can make. So, for example, shown here in the screen capture of my terminal, you see there's a compute partition. This is on expanse at SDFC. There's this CW3 compute partition, there's the CW3 shared partition, this debug partition, this GPU partition. Each one of those has a different set of policies of the types of resources you request and how much you can request, how long the jobs can run, who and even who can run the jobs, right? For example, the compute partition on Expanse is if you're running jobs that require a whole compute node or above, right? So if you need a whole compute node, which is on Expanse 128 CPU cores and above, that's sort of where you go, right? Because you're going to be charged by the node essentially. So every time you need to have one whole node yourself, you would go to the compute partition, request a whole node there. You can see some people are requesting, or I mean, well, sorry, this is the sinfo side. Um, if you need to request, more than a whole node, so maybe you need 2, 4, 8 nodes, right? That's where you would go if you have this sort of distributed memory type of application, MPI-like application you might run across multiple compute nodes, right? Because you're going to be charged by the whole node there. The CW3E partition here is for a specific customer that we have. So this CW3 project, they have their own partition because they sort of bought their own hardware that we run for them. But it has sort of the same policies as the compute. That's why it's just called CW3 compute. Then we have debug partitions that are like for shorter jobs, right? So there's all these different policies that apply for different partitions for different reasons. And so, for example, I put the link here to the Expanse user guide. If you're not familiar, you can look at there's like a table there that shows the different partitions and the different sort of major policy restrictions on, say, how many jobs you can request at any given time, how long the jobs can run. Those are kind of the main sets of policies that you know you as a user would be interested in for any given HPC system that you're running, and what you would want to know about the different types of partitions that are available on the systems that you have. Okay, so now we jump into actual batch job scripts for the last 15 minutes here. I'll try to cover these examples, and there are examples in the copies of the examples in the GitHub repo that I've got listed here for the exercise materials. So if you do have access to either Expanse or some other Slurm cluster, you should be able to run those examples there as well. You might have to modify a few things. We recently used this set of exercises for a workshop too, so I'm gonna probably go through and remove a few extra lines that were used as part of the workshop itself. But you can sort of refer to, these in general as mostly complete and should be runnable on most Slurm systems that you have access to, because they're very simple jobs for the most part, at least these first couple examples. You just need to maybe change the account numbers and the partition that you might have access to. But these are set up to run on Expanse at SDSC if you have access to them, or if you have access to Expanse as a resource. And if not, if you go into the Expanse user guide, we do offer trial accounts. So if you're new to HPC, we can get you set up pretty easily, pretty quickly on Expanse itself by just sending us an email. Okay, so this is the first exercise. It's very simple batch job script, Slurm script. As I mentioned, again, this is just a bash script usually, or usually a shell script that you'll write for submitting to Slurm. On most systems these days, the default shell that you use is bash. So, this first line of the job script itself here is this shebang character sequence that specifies, again, if you're not familiar with shell scripting, right, the hash or number symbol, right, is just a comment. And so this first comment is really a way to tell Slurm how to interpret this text file, right? Because at the end of the day, this is just a text file on the system that you'll submit. And it's just telling the Slurm that, please interpret this as a bash shell script, right? So it knows what to expect in terms of the syntax and things later. This can be other things, different types of shells if you want a different shell, or if you want to even write a Python job script, you can. It's just, this is usually the standard on most systems these days, is to use a bash shell script. So that's not too important, but the next part is very important. These are the Slurm SBatch directives, right? So the SBatch directives are the comments, you can say, you see, that you add into the shell script to specify to Slurm what you want, essentially, right? And other, attach, other attributes that you might want to attach to the job when you submit it This is how you specify that resource request and sort of these other pieces of information that you might want to attach to the job itself. So just quickly running through the SBatch directives here, you see this is usually how I structure mine. I usually start with a job name, right? Usually it's useful to give a specific name to a job that you might want to, just to label your job with a name of like, what is this job that I'm running? Here, this is just a simple example. So it's this, hello, my name is. Um, when you run on Slurm, usually you have to assign an account number to the job, right? So this is for the Slurm accounting. This is what the system is usually tracking. And usually you have a limit to the amount of compute time you have on any given system. So this is how Slurm usually keeps track of it. There's usually an account ID that you have to track that usage to. And so, on most systems, I would say it's usually some sort of Linux group that it's also tied to. So that's how it is on our system. So this is, for me, this is my use 300 group. Yours will be different if you have an allocation on Expanse. There might be a different, syntax to what these account IDs look like on any given system you have. But at the end of the day, usually there is an account that you have to assign the job to. So for counting purposes, right? Next is the partition directive, right? So this is where you select what partition you want the job to run in. Again, this is usually tied to the type of resource you need. In this case, this is a super short job. It's really like a test job. So I'm just running it in our debug partition, right? Because at the end of the day, you'll see on the next 3 lines, all I'm requesting here is I only need this to run on a single compute node, and I don't even need that much. I just need it to run on a single CPU core. So these next 2 lines here, this end task per node is just sort of, this is a serial job because it's just a single command that I'm running, this host name really, and then the sleep command. And then it's not a parallel job, so I just need 1 CPU for that task that I'm running. Obviously doesn't take a lot of memory. So the next directive is just how much memory I'm requesting, 1 gigabyte. On Expanse, the default is 2 gigabytes roughly per CPU core. So this is even less than I'm usually allotted in terms of how much I would get charged for this job. Then you usually have to specify how much time you need for this job to run, right? This is usually one of the more tricky. In addition to memory, time is also usually one of the more tricky ones because many of the times when you're first starting to run your application on a new system with a new type of compute resource, you might not know how much memory a given run needs or how long it'll take. So these need to get usually dialed in over time once you get familiar with the system and how your application runs on it, or how your typical, say, simulation or analysis, takes for the types of inputs and outputs you're expecting. Those things will vary depending on the type of resource you're using, and also the individual job task that you have to run. So usually when you're getting on a new system, hopefully you have some vague idea of how much memory your application will take to run. Usually when I'm working on a new system though, for the time directive, I'll usually just set it to the maximum and then sort of dial that back over time, because on every system, this time request here is usually not how much time you're going to be charged for. It's just the maximum time that you request from Slurm, right? Usually you're charged at the end of the day by how much time you actually consume. So if my job finishes faster than 2 minutes here, right, I will only be charged for the amount of time I use, not the full 2 minutes here, right? So this is just something to keep in mind. And then the SBatch output directive is just sort of how I want my output file to be named, right? So as the job runs, there'll be a standard output, standard error output. This is just the name of the file that I want it to be directed to. And I'll touch on what those symbols mean in a minute or two. Ooh, only got 5 minutes left. Oh, it's going too long. Okay, so So yeah, so this is a simple example. And let me go ahead and show you that on Expanse. So this is what you would see on Expanse when you run this example, right? So this is the sbatch command. This is the command that you'll use to then submit that script to the system itself, right? So here I'm running the sbatch. Hello, my host name is example from the repo. When you submit a job with sbatch, you'll get a Slurm job ID. So this is an important sort of uh, piece of information when you're running your jobs on a given system. If you have a problem with a specific job, maybe it fails, maybe you get some error message in your output files, having the Slurm job ID handy to provide to, say, the help desk team when you need reach out for help is always appreciated, because at the end of the day we have thousands of jobs running at any given time. We don't know what your job ID that you're talking about might have been when it failed, so we can't. It's hard for us to look things up. This is just a key piece of information to keep track of when you're running jobs on the system. So your Slurm job ID. Again, so once you submit your job to the system, you'll then usually check right away once you submit it what the if the system sees it and if it is it running. Our debug partition, if you're using Expanse, is usually designed for pretty quick turnaround. So it's usually fairly idle because you can only run up to 30 minutes or so in the debug partition. So you can see here, as soon as I ran the SQ command to look up my jobs that are um, either pending or running, these basically started running right away on the same debug compute node, this Expanse 955. Yeah, and so once you submit the job to the scheduler, you'll usually run like an SQ. If you want to get specific information about a specific job, you can feed in that job ID to the SQ command with the -J flag. With all of these Slurm commands, there's many different flags and command line options that you can provide to them. The best place to look for the different types of options that are available is in the Slurm documentation for each of these commands. But -U here, -J are pretty common ones that I use all the time. But yeah, there's a whole host of other commands that you can run to get additional information about your job as it's running in the queue. Here at the end, I'm showing you the output file, right? So I mentioned the sbatch directive for the output file. It kind of had these special symbols here with the %x, the %j, the %n. What these are is basically formatting the output file from my job here to label all of the output from the job as it's running to the standard output file that I have is the Slurm job name, is that %x. I want to also track the Slurm job ID for the output, right? Because at the end of the day, if you want to debug things, usually you want to know, uh, you know, probably a human readable name for the job, but you also need to know the specific job ID for the job so you can coordinate what output came from which job, right? If you don't have, say, the job ID in your output file, it's kind of a problem sometimes because maybe you'll just keep overwriting the same output file from different jobs is a common mistake people make. So having the job ID like tied to the actual output file is always useful. And then, it's also usually to know like, oh, what node that did the job run on is also usually a useful piece of information. So that's why this output directive is sort of structured that way, and it's uh, just intended to be good practice. Okay, I think I'm out of time for the slides. But let me see if there's any last quick things that I want to say. I mean, the slides from here on out are pretty, I think, hopefully readable and understandable. The other things that the exercises really cover is just how to structure things after the SBatch directives, right? So, for example, the second exercise here just kind of shows you that at the end of the day, everything that comes after you define the SBatch directives, right? So once you tell Slurm what you want and sort of label the job correctly with Slurm, everything else is just a command or a call to a program that you want to run, right? Usually, though, there's different types of things that you'll want to set up before you run your main program. One thing might be the software environment. So that's sort of what this example is showing. On many HPC systems, there's something called a module environment, and you'll want to set up your software environment before you run, say, your main program. In this case, it's sort of this Py program that I'm running in Python. Other things that you might define in some of the other examples is like environment variables and things that'll help you set up the environment of that job further so that it's sort of easier to run your application, right? And that's really what the remainder of the examples are sort of demonstrating. So yeah, if you have to take off now, I would just say, please go ahead and take a look at the remaining slides and the examples in the batch computing repo here. If you have any questions, feel free to reach out. If you can stick around, I'll try to make a few more comments on the exercises and other parts of the slides that we haven't finished up for people who have to leave. But yeah, so thank you for attending today, and we'll stop here. And looks like there's a few questions in the chat that I'll get to right now. And then for those who can stick around, we'll come back to a couple more of the slides here, and maybe I'll show you actually running some of the examples on Expanse Live.